Redshift effect, a consequence of the expansion of the universe in which radiation from distant sources is stretched towards longer wavelengths. In case of light from galaxies, this appears as a shift towards the red end of the spectrum, hence the name redshift. Cosmic microwave background (CMB). Almost 14 billion years after the Big Bang, the universe still contains a faint remnant of the colossal heat and radiation created during its birth. It is detectable today as more or less constant heaps of microwaves across the whole night sky. This being remnant of infrared radiation heat whose wavelength has been stretched into microwaves by the cosmic expansion. Hubble constant, often also called the Hubble parameter, because it is not actually fixed at all. The Hubble constant measures the rate at which the universe is currently expanding. Current measurements imply that the universe began expanding around 13.7 billion years ago. Scalar field, a kind of quantum force field likely to exist in the very early universe, predicted to have anti-gravitational effects. Scalar field allows the rapid expansion of universe known as inflation, and its collapse triggers the release of radiation and matter characteristic of Big Bang. Timeline. 1917, Einstein applies the theory of general relativity to the whole universe, but finds it fails to give the right answer of a static everlasting cosmos. 1922, the Russian theoretical meteorologist Alexander Friedman finds equations showing GR allows a non-static universe. A doubtful Einstein eventually concurs. 1927, prompted by the redshift data, the Belgian cosmologist and priest Georges Lemaitre argues that GR implies a universe which had a beginning. 1929, American astronomer Edwin Hubble announces discovery of the expansion of the universe, with galaxies racing away from each other as if from an explosion. 1946, George Gamow, Ralph Alpher, Robert Harman began study of the creation of chemical elements in the Big Bang. 1948, the steady state theory is proposed by Hermann Bondi, Thomas Gold, and Fred Hoyle at Cambridge University, who argue the universe does not change over time. 1950, Fred Hoyle coins the term Big Bang in a series of BBC radio lectures meant to be derisive. It becomes a standard description of the theory. 1964, engineers Arno Penzias and Robert Wilson at Bell Laboratories detect the cosmic microwave background (CMB) seen as confirming the Big Bang theory. 1970s, Soviet theorists Andrei Lind and Alan Guth in the US highlight the role of scalar fields in triggering inflation in the very early universe. 1992, Kobe satellite studies CMB microwave background in unprecedented detail and begins a new era of high precision cosmology, with reliable estimates of many universal properties. Studying exploding supernovas, astronomers find convincing evidence for the existence of dark energy, which is now thought to dominate the universe. How will the universe end? The discovery of dark energy has profound implications for the future of our universe. Cosmologists once thought that the fate of the cosmos would be determined purely by the density of matter in the universe. If this were high enough, gravity and even usually halt the expansion, prompting a collapse back to a cataclysmic big crunch. Otherwise, it would expand for forever. It is now clear, however, that dark energy has been the dominant force in the cosmos for the last 7 billion years and is driving the acceleration at an ever increasing rate. As such, the universe looks set to expand for forever. If so, our universe also looks to become a very desolate place. For example, our galaxy will find itself entirely isolated within the next 100 billion years, the rest of the cosmos having been transported to regions in so far away that light can never match us. Uncertainty principle. The relationship between properties of subatomic particles